Now let's see the next topic, that is moving coil galvanometer. So we have already seen what, or that there is a torque, there is a resultant torque on the current carrying loop, rectangular loop or any kind of loop. There is a torque, or that current carrying conductor experiences a torque. Total force is zero, but it experiences a torque when it is kept in a uniform magnetic field, right? So what is the condition for that torque? There should be a uniform magnetic field. It should have some current in it, and when it is placed, it will experience a torque. Expression for torque also we have seen. Now this particular concept is actually also used to determine the availability or the presence of current in a given circuit, right? So if you draw current from that circuit and you are able to make that current pass, suppose if this is the as you can see here, this is the external circuit. There is a E is nothing but the EMF of the cell, right? And these are the leveling screws. This is actually, you are actually seeing this galvanometer, side view of this galvanometer, right? So screw through which it is leveled, that is leveling screw. There is a key here. So if you press this key, there will be a current flowing in the circuit. Otherwise, there won't be any current. So when there will be a current flowing in this circuit, you can see there is this T, right? The T which is written here. This is also called torsion head. So basically that is a metallic screw through which the current is made to pass through this. Now here you can see there is PBW. We will try to understand this, the importance of this as we'll go through this. But this is actually phosphor, bronze wire, right? Okay. And then you have this M, which is nothing but a mirror. We will see the use of this as well, but right now the main concept is here. This is the main thing, right? So what exactly is here? Here there are two magnets, right? One side you can see there is the north pole which is visible. On the second side it is south pole, and it is kept like this, such that the magnetic field between these two poles is always constant. So that is what being achieved here, so that it is a uniform magnetic field. Okay, and in between you can see this gray part, this rectangular gray part, PQRS. These are nothing but the rectangular coils in which the current, if it flows, if the key is closed and if the current flows in this outer circuit, this will also flow in that rectangular coil. So now that coil becomes a current carrying conductor, or may not be a current carrying conductor depending on whether, or current carrying coil depending on whether there is a current flowing in that circuit or not, right? And what do we know about the torque? We know that the torque in that particular rectangular coil will be given by N I A B sine phi, where phi is angle between the area vector and the magnetic field. So you can see there is a magnetic field between north and south pole. There is this area as well. This rectangular coil will have an area. It has number of turns. Now whether there is a torque or not, it will only depend on the current. So if there is a current, there will be a torque. If there is no current, there won't be any torque. If there is a torque, the current carrying conductor will rotate, because that is the property, that is the main task of torque. It tries to rotate something, right? So the torque will cause this rectangular coil to rotate. But here, as you can see, after that there is a hairspring, or simply spring, right? So what does it do? When the rectangular coil will rotate, this hairspring will oppose that, and due to that there will be a restoring torque which will be restored or which will develop in this hairspring, right? So there will be a restoring torque in the coil. So the torque in the coil, the restoring torque, there is just like restoring force. If you remember restoring force you must have studied in 11th standard, that is equals to kx. So force was directly proportional to what? X, the displacement. Similarly, there is restoring torque as well, and restoring torque is equals to K into alpha, where alpha is the rotation, the angle by which this rectangular coil rotates, or you can simply say this alpha is nothing but the twist in the coil. I hope it is clear. Okay, so ultimately what will happen, this restoring torque does what? It opposes the twist in the coil. So ultimately at equilibrium, these two things will be equal, right? The torque, the original torque experienced by the coil is due to the current and the magnetic field. So if there is a current, coil is kept in a magnetic field, it will experience a torque. Due to that torque, the coil will rotate. And when that coil rotates, due to that rotation, there will be a restoring torque developed in the or established in the spring. Due to spring, there will be a restoring torque as well. And due to that, what will happen? That is an opposing torque. This is the torque due to the current is the original torque, so or torque due to the magnetic field and current. And there will be a time when the external torque and the restoring torque, they both will be equal, right? That is nothing but equilibrium. So at equilibrium, what will happen? At equilibrium, these two torques will be equal, right? So torque will be equal to restoring torque. That means NIAB sine alpha will be sine phi, let's say that is the angle, sine phi will be equal to K alpha, where alpha is the twist. So from this, we can say that whether current is there or not, that can be easily, we can easily say that if from this expression, that is I is equals to this K divided by N A B sine phi into alpha. Alpha is the twist. Phi is the angle between area vector and the magnetic field, right? So now this is the expression for current. Now there is one problem here, that is this sine phi. Phi is angle between area vector and the magnetic field, which keeps on changing. So that means that whether there is a current or not, it will also depend, I mean, the torque becomes zero even if phi is 0 or 180 degree. So in that case also, right here, we said torque is equals to NIAB sine phi. We said that if N is okay, A is okay, B is okay, but what? This should measure only the presence of current. If there is no current, torque should be 0. But here what will happen? Even if phi is 0, sine phi will be 0 and torque will be 0. So torque is right now dependent on I as well as sine phi or phi. We need to eliminate this dependency of current on angle. Otherwise, this device, we won't be able to use it for our purpose. I hope you are understanding that. So in that case, what we or how to eliminate that? So that is done using a special type of magnetic field called radial magnetic field. So instead of having plain magnets or plain magnetic poles, if we have a curved magnetic force, magnetic poles like this, then if you see now the magnetic lines of forces, they leave the North Pole, enter into the South Pole, and it will be like this. And if you see the coil, at any point of time now, if you see this, the angle between the plane of the coil and the magnetic field is always zero at any point of time. At this particular instance, you can see the magnetic field is just touching the surface. These are the line, right? You can see here, what do you see here? Magnetic field lines, the blue lines, has just touched the red surface of the coil. Similarly here, you rotate it by any angle, you will see the same thing. That is the field, right? B is parallel to or just touches the surface. So if it is parallel to surface, that means what? It is perpendicular to area vector. That means phi is how much? Phi is always 90 degree. So this type of magnetic field is called radial magnetic field. What is the use of this? You can see here. The phi value is now always 90 degree. So phi is constant. So that means what? That means now the torque depends only on current. If there is current, there will be a torque. If there is no current, there won't be any torque. If there is a torque, there will be rotation of there will be a twist in the coil. Otherwise, there won't be any twist. If there is a twist in the coil, there will be a value of alpha. Otherwise, alpha will be 0. So that is how this radial magnetic field helps us. Right? So this, what you are seeing here, right? It is the top view. We are seeing it from here. So there it will look like this. It won't be plane. It won't be a plane surface North Pole and plane surface of South Pole. It will be a concave surface if you see from the coil side. So that's why the magnetic field will be like this. Okay, so the angle between the plane of the coil and the magnetic field is 0. That means phi is 90 degree. And that's why sine phi is sine 90, which is equal to 1. And now this expression for I will be what? It will be K divided by K divided by NAB. Sine phi is gone, that is 1 into alpha. Now if you see this expression, I is directly proportional to alpha, where alpha is the angle. Now this can be rewritten as I equals to G alpha, right? What is this G? This G is very important. This is called the galvanometer constant. And what is its value? This G is equals to K divided by NAB. If you see, K is nothing but the spring constant of that hairspring. N is what? Total number of turns of in the coil. A is the area of cross section of the coil. B is the magnetic field. Now in the box, if you close this setup in a box, these 4 values are fixed. You are not going to change the spring. You are not going to change the number of turns, the area cross section, and the magnetic field strength. It's not going to change for a closed, finished or final device. So this will be fixed, and that's why this G or this entire expression will be a constant, and that is called galvanometer constant. So this is fixed for a galvanometer. Okay, now this is called the galvanometer constant. So what happens now? Now only calibration is left for this device. So there will be a rotation in the coil, and when this coil rotates, you will be able to see that rotation from the mean position using this arrangement of mirror. So that is the purpose of this mirror. So it shows that phosphor bronze wire, right? How much it has deviated. That reflection you can see in this mirror. That is the purpose of that mirror, to show in reflection the how much deflection or how much twist is there, basically the alpha value. So if there is more twist, it simply means what? It means there is more current. If there is less twist, that means there is less current. If it is zero, that means if there is no twist, that means there is no current, right? So this calibration, proper calibration, we have to do that. How much or what is the amount of current? If we have to measure that also, galvanometer only detects. You can only get an idea whether the current is flowing in right direction or left direction, whether the amount of current is more or less. You can only compare two things. If you have to find the actual values, you will have to calibrate this device, that you will have to see for what is the maximum value of twist it can show, and at that time what will be the maximum value of current in that. So that ampere and this twist, and then as it is directly proportional, so you can mark those points, 0 ampere, maximum how many amperes, and then you divide them and calibrate them. Okay, that is how it is done. Now whenever such devices are there, we also have something called, or a property related to those devices, called sensitivity. Sensitivity is what? See, if you have a device which shows more deflection for the same amount of current, that means we will say that that device is more sensitive towards the current. It is showing more deflection. Now, if there is more deflection for a very small amount of current, it is good for me to observe. As an observer, if I have to observe it, it is good for me, because there is more deflection for less current, right? So accuracy will be more for an observer when I'm measuring it. But due to that, there will be a limit on the maximum current which I can measure. So this sensitivity is very important, right? This sensitivity, which just now we discussed, it is very important. What is sensitivity? So how much sensitive your device is to the input current or input voltage. So deflection per unit current, deflection is what? Phi. So phi per unit current, that is nothing but current sensitivity. So there are two types of sensitivity. One is current sensitivity and the second one is voltage sensitivity, right? We know that I is equals to K divided by NBA alpha. So from there you can say alpha by I will be what? It will be NBA divided by K, right? And we have to find voltage sensitivity. So voltage is what? It is IR. So if you have to find voltage sensitivity, you will have to find, so this is current sensitivity. If you have to find voltage sensitivity, you will have to find alpha divided by IR, that is alpha by V. So if you have to do that, here also you will have to do the same thing, that is this divided by KR. Now R is external resistance, so we cannot do anything in that. This is what is two types of sensitivity. So here you can see, more the number of turns, more sensitive will be the, or more deflection per unit current you will observe. So this sensitivity is directly proportional to M, directly proportional to magnetic field, directly proportional to the area of cross section, and it is inversely proportional to the spring constant. So more spring constant, less sensitive galvanometer. So that's why the spring which we have kept, this is, we need high sensitive device, so that even for a very small deflection, very small value of current, there is a good amount of deflection. That is why we need good sensitive devices. Otherwise, it may be possible that you are having a very small amount of current, but because spring is very tight, that's why it is not able to show you any deflection. The spring is not letting the device rotate, right? So that's why Soft springs are used in sensitive galvanometers. Softer the spring, more sensitive will be the device, means there will be more deflection for a very small amount of current as well. So that is the sensitivity, and two types of sensitivity. Next very important topic in galvanometer is that the same galvanometer can be used as an ammeter as well as a voltmeter. So next is conversion of these galvanometer device to ammeter and voltmeter. So let's say G2A, that is galvanometer to ammeter, and next we will see galvanometer to voltmeter as well. So you should know first the purpose. Ammeter's purpose is what? To measure current, right? And voltmeter's purpose is to measure potential difference. Now, how do you convert it, or why there is a conversion even required? So we'll see that. Now, see, current means what? It actually means flow. So you will have to, I can give you an example related to this, is your water meter. The meter which is connected to the water connection of your device. Now, meter is a device which is used to measure the flow. So it should obviously come in the path, right? Otherwise, how will it be able to measure the flow? But when it is coming in the path to measure the flow, it should not consume water. It should let the water flow. It should only measure. It should not consume. Any device, right? So that is the main thing which we have to understand here. So it has to measure the flow. So now if there is a if there is a, say, let's say, if there is a wire in which there is a current, you have to measure whether there is a current or not, or how much current is there. That can be done using the ammeter. So how your device should do what? It should actually stand there on this path and measure how many electrons are flowing per second. So it has to go and sit in that path, but it should not disturb the flow. I hope you understand. It has to be there, but it should not disturb the flow. So what it will do, here is my galvanometer. I'll keep it here in the path. So that means the current in which, and the wire in which the current is flowing, this galvanometer will go and connect to that wire. But it should not consume that current. Otherwise, there won't be any use of this, right? So what should I do is, I'll actually connect it to another resistance, right? Basically, this is nothing but bypass. Okay, this bypass, let's say, we actually use the word called shunt for this. Shunt is a resistance in parallel. So I actually connect a shunt or a parallel or a resistance in parallel to the G, right? What about this? This S has to be very small value. Why we are doing that? So if I keep it small, most of the currents will actually pass through this. That is what resistance is, right? In current electricity, you must have studied. Current, if there are two available options, one with high resistance, one with less resistance, so that means what? In high resistance there will be less current, in low resistance there will be more current. So that's what happens here as well. In this section, that is G section, the current which will flow is Ig, while most of the current will flow through this, let's say that is I minus Ig, right? So this is the ammeter. This is how ammeter is made from a galvanometer. Now this entire thing can be kept in a box. This will become your ammeter. That's all. Okay, so that is what this this is how this ammeter is converted from a galvanometer. Now, if you want, you can apply the Kirchhoff's laws here, and you will see that I minus Ig current flows through this shunt resistance. So there is a drop, and that drop will be equal to Ig into G. G is the resistance of galvanometer. So both the potential drops obviously should be same. So generally you will be asked in this, how much shunt, how much uh, resistance should be added to a galvanometer to make in an ammeter, and in what configuration, whether it should be connected in parallel or serial combination, series combination or parallel combination. So as you know, if it has to be converted to ammeter, it has to be in series, it has to be in parallel, and that parallel resistance S is equals to Ig into G divided by I minus Ig. So how much current, on what all factors this shunt will be decided, that what is the maximum value of current you want to measure, and what is the current that will flow through that galvanometer, right? So once you know all those things, you will be able to find the S. Basically, this is the important thing here, that you should know how much maximum current you are going to measure. So based on this, you can decide what will be the value of this shunt resistance, or simply shunt. Now, how to convert a galvanometer to voltmeter? So let's understand that as well. So if there is, voltmeter does what? It measures potential difference. That means there is this circuit in which you have two endpoints. Let's say this is one point and this is another point. Across this, you have to measure the potential difference. We know that the potential difference will be equal to what? It will be equal to the I, which is the current which is flowing into this, into R, which is the resistance of this, right? But what we, so that is, if we know the I and R, we can just do the calculation and we can find out. But here we have to make a device to do that. Okay. So obviously, if you have to measure difference between these 2 points, so you have to connect your device to these endpoints. No doubt in that. So whatever is your device, let's say galvanometer, has to come here. It has to be connected to those two ends. Here you had to measure the flow, the rate of flow. So you will have to be part of the flow. That's why galvanometer is in the wire in which you have to measure the current. It is in that path. But potential difference, you have to measure the difference between two properties, difference between the values of a property at two different points. So you should be able to monitor those 2 points. So that's why this is connected like this. Okay. Now the galvanometer, if you have to connect, if you have to convert it to voltmeter, this, now what should I do? The galvanometer, see, if galvanometer's resistance is very low, right? You see there is only a coil, its resistance will be very low. And if this is the case, if the external resistance is very high, then in that case, most of the current will flow through the galvanometer. Now you have to measure the potential difference. You don't have to consume the current. So because you don't have to consume the current, so what you have to do with the galvanometer, you have to have a very high resistance. So why it is very high here, why it is very small here, I guess you already know now. In the first case, right, in the first case, the galvanometer should not consume the current. So we are giving a bypass to the current in which the resistance is very low. In the second case, galvanometer again should not consume most of the current. So that's why with the galvanometer we have attached a very high resistance. So the resistance in the outer circuit is always less than the resistance in the circuit which is connected to the galvanometer. So in the path of galvanometer, there is a high resistance. So now again, it will not consume most of the current. Most of the current will again pass through the original path, right? So this is the thing. So as you can see here, in the first case, galvanometer and the resistance, extra resistance or the shunt which we have used, that was a parallel combination. Here it is very high resistance in the connected in series with the galvanometer. That's all. Now, whatever is the potential difference across the 2 points, let's say A and B, the same will be across this G as well. So that means if this potential difference is V, we can say that this V is equals to the current which flows through this galvanometer, let's say that is Ig, right? So that will be equals to Ig into G plus R. That means what is that value of R which should be connected to G? So that R should be equal to V by Ig minus G. Right? So again, based on how much total potential difference your voltmeter should be able to, maximum potential difference you want your voltmeter to measure, that is V. Based on that, you will decide what should be the value of resistance, which you have to add in parallel, in series with the galvanometer to convert it into voltmeter. So that is how galvanometer can be converted to voltmeter and ammeter. In case of ammeter, a very small resistance in parallel to the galvanometer, and galvanometer has to be connected in the wire in which you have to measure the current, because it has to measure the flow. In the second case, galvanometer has to measure the voltage difference between 2 points. So it has to be connected to both the 2 points. That's why it will be in parallel. But it should not consume the current. So that's why a very high resistance should be added in series with the galvanometer so that the Ig is very low. Right? Based on this, you have these two expressions, which is used to determine or to find out the appropriate value of S and R. S means the shunt, very low resistance. R means the resistance which will be connected in series with the galvanometer, that is very high. Right? So that is about the galvanometer, all the concepts related to galvanometer. Okay, now in next class, we'll discuss few more topics about alternating currents. So that we'll do in the next class.